Waves have energy. Whether it's sea waves, the light waves of a laser beam cutting through steel, waves in the Earth's crust causing earthquakes, or the waves which made the Tacoma Bridge shake itself apart in 1940. To take a closer look at how they behave, waves are best studied in a tank of water. The water appears to be moving from right to left. Pushing a dipper into the tank at one end produces a series of simple waves. The waves move along, but place a float in the water and it stays where it is. So what is moving, and in what direction? To look at waves in more detail, models have been devised to help explain their motion. Focus on just the orange spot and you'll see that it moves up and down. It oscillates. Although the waves travel from right to left, the particles on the surface of the water are simply bobbing up and down. This movement is at right angles to the direction in which the waves travel, so it's called a transverse wave. These waves are both transverse, but they look different. The difference is the distance from one peak to the next. It's called the wavelength and is measured in meters. The top wave has double the wavelength. Another characteristic of a wave is its frequency, the number of complete waves which pass a particular point every second. Change the frequency and see what happens to the wavelength. How are frequency and wavelength related? You can produce a simple transverse wave by moving a spring from side to side. Another type of wave is given a different name. This time a pulse is sent along the line of the spring. It's called a longitudinal wave. Fix a marker to one part of the spring and you can see that once again there's an oscillation. But this time the motion is backwards and forwards. For both types of wave, energy is transmitted along the spring, but the spring itself doesn't move forwards. Energy is transferred, but matter isn't. Light waves and water waves are both transverse. Sound waves are longitudinal. They're a series of compression waves travelling through the air. Earthquakes are caused by both transverse and longitudinal waves travelling through the ground. Reflections happen when light hits a surface and bounces back. Pool balls can be reflected too. Imagine you could follow the path of the white ball. A line drawn at right angles to the cushion is called the normal. The angle of incidence is the angle between the incident path of the pool ball and this line. The angle of reflection is the same as the angle of incidence. Sometimes light behaves like a particle. Other times it behaves as a wave. A ripple tank allows the reflection of waves to be studied in the lab. An automated dipper creates water waves which travel across the tank from left to right. A bright light shining through the waves casts shadows on the floor, forming a series of white and grey stripes. A closer look at the shadow of the metal plate in the tank shows the pattern of the reflecting waves. These are the wave fronts approaching the plate. The waves reflected from the plate have changed direction. As with the pool ball, the angle of incidence is the same as the angle of reflection. Some magic tricks are more obvious than others. The cocktail looks real enough, but where is it? Reflection of light can be used to create all kinds of illusions. From the top, you can see that the cocktail is carefully positioned at the side, out of sight of the audience. The magician's hands are behind a sheet of glass. The glass is placed diagonally across the stage and acts like a mirror. When a light shines on the cocktail, the light rays bounce off it. They hit the glass sheet and are reflected towards the audience. A virtual image appears on stage. Switch the light off and the image disappears. While theatres use reflection of light to create illusions, ships use the reflection of sound to measure the depth of the sea. The echo sounding system is called sonar. High-frequency sound waves, known as ultrasound, are sent downwards from a transmitter in the boat. The arrival of the reflected wave is detected. By knowing the speed at which sound waves travel through water and the time it takes for the reflection, the distance to the seabed can be calculated. The depth of the sea is represented on a computer screen. Each tiny dot is a fish, which has also reflected the sound waves back. Bats use ultrasound too. By emitting ultrasonic waves, they can judge how far away an object is, simply by the time it takes for the waves to bounce back. The reflection of ultrasound is also used in hospitals to create an image of an unborn child. It's a safe way of monitoring the baby's progress. Other waves can be reflected too. We rely on the reflection of radio and microwaves for worldwide communication. Satellites in space receive signals and reflect them back to Earth. These are collected by satellite dishes. But why are the dishes this shape? And why is the receiver positioned a short distance away? To see how a curved dish collects and focuses a beam, a heat source is placed some distance from a parabolic mirror. In front of the mirror are 3 matches in a row. But only the middle one ignites. The heat rays arrive at the curved surface and are reflected inwards. Wherever the rays strike, they all reflect to the same central point. This is the focal point of the dish. Light travels in straight lines. Shining a powerful light source through a thin slit produces a straight, narrow beam. Place a glass block in its path and the beam starts to behave differently as the block is rotated. Some of the light is reflected. The rest passes into the glass. The light bends in one direction as it enters the block and in the other as it emerges from the lower edge. This shift in direction is called refraction. To work out what's happening, think of light as a series of waves. This ripple tank uses a dipper to send parallel water waves across its surface. Putting a plastic sheet into the water makes this part of the tank shallower than the rest. Waves travel more slowly in shallow water. This change in speed changes the wavelength. The wavelength on the top is shorter than the one on the bottom. When the sheet is at an angle, the waves also change direction. The wave fronts bend as they reach the plastic sheet. To understand how speed can cause a change of direction, imagine a truck approaching marshy ground. If the marsh is at an angle, the right wheel slows first. The left carries on at speed for longer, swinging the truck round. So when light hits a glass block, it changes direction because it changes speed. Place a glass trough in the beam, and you can see how water also affects the path of light. The bending of light helps explain why this apparently straight stick is in fact bent. While this bent stick is actually straight. Refraction tricks our eyes, making us think that the stick is nearer the surface than it actually is. These gannets have to take this into account when they're diving for their underwater prey. Pass a ray of light through a semicircular glass block, and again it's both reflected and refracted. This happens at the straight edge. As the block is rotated, the angle at which the refracted ray leaves the block changes. Eventually, there's no refracted light. Instead, all the incident light is reflected back inside the block. This is known as total internal reflection. At a certain angle, the light stays inside this plastic rod. Total internal reflection allows light to travel through a curved shape. A laser beam can even be made to travel along a curved stream of water. Optical fibres work by the total internal reflection of light. As well as being decorative, they also have practical uses. Telecommunications rely on total internal reflection to transport information along cables underground. To take a closer look at how they behave, waves are best studied in a tank. Waves have energy. Whether it's sea waves, the light waves of a laser beam cutting through steel, waves in the Earth's crust causing earthquakes, or the waves which made the Tacoma Bridge shake itself apart in 1940. tank of water. The water appears to be moving from right to left. Pushing a dipper into the tank at one end produces a series of simple waves. The waves move along, but place a float in the water and it stays